Hello and welcome to the 21st lecture of Introductory Astronomy. Today we're going to be talking about the entire universe as a whole, the geometry of the universe. It's going to be really, really interesting. There is no studio audience today because I am recording this lecture directly after the last lecture, lecture 20, because I'm going off on a speaking engagement later this week. Still though, this is really exciting stuff. And so let's just go right to the slides here. That's why I'm still wearing the same sweater, by the way, because I don't wear the same sweater every day, but I didn't bother changing it. So this is Physics 1600 at Michigan Technological University, Introductory Astronomy. This is lecture 21 in the series. There are a few more to go. I don't remember exactly how many, like 2 or 3, maybe 4 more to go. Talking about the entire universe, the geometry of the universe, and what's in the universe this time. So I am Robert Nemorafo. Next time we're going to be doing the very beginning of the universe. That'll be fun. So if you're taking this course for credit, you need to go to courses.mtu.edu. Otherwise, just sit back and throw stuff at the screen. Okay. If you're taking the course for credit, you should pay attention to the lecture. You should track down the listed Wikipedia entries, but not when they involve higher math. You should check out the astronomy pictures of the day posted during the semester, all the way from early September through mid-December, but I'll be reviewing some at the end of this lecture that are not necessarily relevant to this week's lecture, but they're just, the APODs are just relevant generally to what's going on in astronomy. If you're taking it for classes, for credit, you need to have completed quizzes 1 to 10 and just wait, do the best you can, remain calm while homework 11 will be released later today, assuming today is Wednesday when you're seeing this, although it's Monday here in right now for me. So go to courses.mtu.edu, please. So things to check out on Wikipedia. Entries named shape of the universe. Give an overview of what we're going to be covering. 2, redshift, dark matter, dark energy, and age of the universe, which we talked about a bit last time. I think we might run a little bit short today, but we'll see. Some strange stuff going on in today's lecture, some really strange things when considering the universe as a whole. So the universe, as I said last time, is too complex to consider all the things in it, so we have to simplify it somehow. So the way we simplify it is we smooth it over in our equations and say the universe is just the same smoothness everywhere. And not only that, but according to the cosmological principle, it appears the same from every place in the universe. Not only that, it's isotropic. It appears the same in every direction you look. And if you were to move to another place in the universe, it would again look the same in every direction. And that is what homogeneous and isotropic mean, and they were described also last lecture. Okay, so when describing the universe as a whole, we talk about its geometry. And what do we mean by that? Now, geometry, many times you remember from math class, being triangles, X, Y, Z, right angles, things like that. And typically when you did that, you considered things as they appeared on a flat piece of paper. And that is called Euclidean geometry, or one way of thinking, it's also a flat geometry. So in flat geometry, you can draw a circle like this. I just like write on top of things now. In previous years, I was careful not to write on top of things. I don't care anymore. So just look at the red, tune out the rest. And so here we have a circle that has an area that's well known. It's if you were to compute the area of this, it would be pi r squared, where r is the, let's go to another color, see if that works, where r is the radius of that circle. So we're most familiar with that. So now let's talk about spheres, which are the next, a three-dimensional thing of a circle, of approximation where everything is all equidistant from something. Here it is. Here, everything on the perimeter of the circle is equidistant from a point in a nice flat sheet. But if you go to 3 dimensions, you can get a sphere. And you can many times tell spheres in textbooks because they have a little window drawn on the lower left, usually, which indicates that it's reflecting a window in the photograph, which doesn't exist. But anyway, this is a sphere. And in nice normal flat space that we've been taught in school, you can take the volume inside that sphere and you would find that it's 4/3 pi r cubed. Again, nothing new. So now let's say that, let's go back to flatness and talk about 2D for a bit. Let's say now that you have a big circle that so originally you have your nice flat sheet of paper and you have a nice small circle, and sure enough you compute the perimeter of the circle, you calculate the radius, and you find the area is pi r squared. Now let's draw a bigger circle, a circle as big as the room. If you do that, you will find that circle also has an area of roughly pi r squared. Now let's draw a circle as big as your city. So let's say you live in Houghton, Michigan. You can draw, it would have, a couple kilometer radius. You could get out there with paint, do it at night so you don't get in trouble. I guess you could try to paint everything in the middle of the circle, find out how much paint you needed compared to the radius of the circle would be pi r squared. Pretty close for a city. Now, however, let's say you go out and do a continent or do a fraction of the Earth. So now picture that this is the Earth. And you're this part. So now let's do this part of the Earth. At this point, the curvature of the Earth becomes important. When you do a significant fraction of the Earth, the curvature of the Earth, and so if you were to find the area of that circle, you would find it's not pi r squared. The curvature of the Earth makes it, actually, I think it's less than pi r squared. No, it's greater than, depending on how you measure r, greater than pi r squared. It's also possible to have, no, I think it's actually less, sorry. Hopefully I have my terms negative and positive curvature right. But I think it's less. But there is possible also to have something called a saddle point on a curving surface where the area of the circle is greater than pi r squared. Similarly, it's possible to have spheres if you have a curved geometry where the volume is different than 4/3 pi r cubed. Now, this means that there's some kind of strange curvature, and Einstein was famous for incorporating his geometries, these strange Riemannian curved geometries, and trying to explain things with them. And he was very clever in doing that, and has come up with the best version of gravity and the best explanation for cosmology yet. But in this case, spheres, if they have negative curvature, you find a sphere, it has a volume of greater than 4/3 pi r cubed. If it has positive curvature, its volume turns out to be less than 4/3 pi r cubed. So we can go out and we can do things like defining volumes in the universe out there and estimating radiuses and counting up number of galaxies there. And in a sense, what we're doing is we're estimating the volume there. So one way of determining the curvature of the universe is by going out and measuring it and seeing if we get far away from our own galaxy, whether our universe has positive curvature or negative curvature, or whether it's flat. If you did this on the surface of the Earth, to remember, if you did it for small enough, you found that the Earth would be flat. But if you did it for big enough, you'd find that the Earth has curvature. What's true of the universe? Does the universe have curvature, or is it flat in terms of volume? Here are some pictures again. You can do this with triangles. This is also in Wikipedia. So if you were to draw triangles here, I believe circles are better than triangles here. I think this triangle has area less than you would expect on this flat plane. This one has more. So this is negative curvature. This is positive curvature. If I have them backwards, it's okay. I think the concepts are more important than the exact nomenclature. Oh, so here we're discussing what it is I did. So I already went over this one. Small circle on your paper, circle size of Houghton, circle size of Earth. So we can go right to the next one. Again, we've done this before. Okay, so when considering the universe as a whole, curvature is important. And we want to know what that curvature is. Is it flat, is it negative, or is it positive? It turns out in Einsteinian gravity that there is a parameter that is important for determining that, and that is the average mass energy density called omega. If that mass energy density is right at the critical amount, which is defined by this, Hubble's constant, pi, which is 3.14159, and then g, which is the gravitational constant, which occurs in Newtonian gravity, F is equals gmm over r squared, then if the density is exactly that critical density, then you get a flat geometry. And spheres have volume of 4/3 pi r cubed. If it is negative curvature, then the average energy density is less. Positive curvature, average energy density is more. So this quantifies the universe and shows that curvature and density are related. Now let's assume a universe that was commonly assumed only a decade ago, that the total energy density of the universe is only made up by the matter density in the universe. So matter that gravitationally attracts like you and I do, like the Earth does, like the sun does. So we're assuming that that's the only type of matter that can be in the universe. Now, if that's true, then we get into some pretty easy to understand universes. One is the open universe. In the open universe, the matter density, and hence the total energy density, is, I think I have that backwards, is less than 1. I think it's greater in that case. So for the open universe, you have a low amount of matter density. In that case, it turns out the universe is infinite in size. Now, we can only see out to the visible universe, but we would then guess that there was a universe that's much further out there than we can see. Again, this infinite becomes, tells more about the limits of our knowledge than something that might actually be true. The universe then becomes larger than anything that we can measure or guess or tell from the equations of even Einsteinian gravity upgraded to explain the universe as a whole. So it's effectively infinite so far as we would know. And in terms of the mathematical model, mathematically it would be infinite. Whether it really is infinite, don't know. But in this simple model where everything is smoothed out all over the universe, all matter is regular matter, and it's open because we don't have that much energy, then the universe is infinite in size and will expand forever. This means that there's not very much gravitational attraction in the universe to keep the universe from expanding. So galaxies are not that massive. There's not that many of them. They don't pull on each other all that much. Therefore, the universe just keeps expanding. The gravitational attraction of galaxies moving away from each other is not enough to stop them from moving away, and it just expands, expands, expands. It's a little bit like the Newtonian analogy of taking a tennis ball and throwing it off the surface of the Earth. It has enough energy to get off, and here all the particles in the universe are essentially tennis balls that have enough energy to get away. And that would be an open universe. Another possibility is we have a dense, closed universe. In this case, there's just lots and lots of energy, of mass everywhere. So much so that it's impossible to throw a tennis ball off the surface of the Earth. Everything just falls back. And even though the universe is right now, all the things are moving away from each other, there's so much gravity in the universe that it's all going to eventually stop and fall back on itself. It'll look the same from everywhere. But the universe would then be falling back, and it would be called a closed universe. This universe is actually finite in size. You could have a set size that we don't know yet. In this strange universe, light can actually circle the universe and come back to where it starts. Now, how can that be? Well, again, picture the surface of the Earth. On the surface of the Earth, if you go around far enough, the curvature of the Earth becomes important enough so that you curve around and you can come back to exactly where you start on the surface of this Earth. The same is true in a closed universe. You can go out and eventually come back to where you started. In this universe, the universe will continue to expand like it is now, and then it'll stop, and then things will start coming back toward each other. And instead of everything being redshifted, everything will be blue shifted. Eventually, everything will start colliding again. All the galaxies will collide. Eventually, even the stars in the galaxies will collide. You'll get one very hot mess that keeps contracting. And what you get is called a big crunch. And I will review that slightly later. It could be, though, that we're right in the middle. That if all energy density is matter density, There could be just enough so that we're right between, exactly between open and closed. If that's true, then Euclidean geometry seems to hold. Universe is infinite in size, well, bigger than we can tell. Always was and always will be, just like it was before. However, the universe is slowing its expansion, and it will just stop expanding at infinite time. That would be the flat universe. So here is a map of what happens. The Big Bang happens here. If the universe is closed, this all dominated by matter energy, the universe would take this trajectory as time goes this way. The universe would have a maximum size here, which could be considered to be the average distance between galaxies as an average larger, and then the average distance between galaxies would start to decline once we got on the far side and started moving toward the big crunch. Then we hit something here. It could be that the universe bounces at the big crunch, and we have another bounce. And it could be this next bounce will be similar to the last bounce. There are models of cosmology which that happens, and those are becoming increasingly popular these days. This is the unbound one. There's a Big Bang, and the universe just expands. The average distance between galaxies just becomes greater and greater and greater until even the galaxies go away. And here's the familiar case of flatness in the middle, the marginally bound case, where Euclidean geometry holds. So what we found is something pretty strange. As of about 10 years ago, rumors started coming in that the universe was stranger than people had imagined in the previous frames. People were looking at supernovae. They had gotten the technology and waited long enough to see supernovae occurring far out into the universe, and were able to identify what type of supernova these were. And they were standard candles because we calibrated them out through Cepheids. And we were finding that these supernovae were intrinsically probably just as bright as they are here, but they appeared to us to be unusually dim. Why are they so dim? And the further out they were, the more unusually dim they would be. And it didn't make sense with a universe where all the matter was in just normal matter like us. Baryonic matter, or in just gravitationally attractive matter like we're used to. It only made sense if the universe had something called a cosmological constant in it. And not only that, but most of it was a cosmological constant. Now this was really strange. Cosmological constants have been hypothesized before. In fact, one can go back all the way to Einstein to see the first serious suggestion of a cosmological constant. I'll write it out, cosmological constant. So Einstein realized that a certain type of cosmological constant, the kind that we have today, gives a pervasive repulsive force to the universe. And he thought that at first would be bad because our universe wouldn't have any reason for that. But then when he talked to Hubble, when he read Hubble's papers, he heard the universe is expanding. And Einstein thought, wow, that's amazing. But before Einstein heard that, he was worried that our universe would just collapse in on itself because it had all this normally gravitational matter that wants to attract itself. So our galaxy wants to attract the next galaxy, which wants to attract the next galaxy, and if you let it go long enough, everything just pulls itself together. So Einstein hypothesized that there was a cosmological constant all throughout the universe, a pervasive, repulsive type of gravity that just exactly balanced the contraction that would have been caused by the normal matter. When Einstein heard about Hubble's expanding universe, he then said that this cosmological constant that he hypothesized was his biggest mistake. Nowadays, we're not so sure it was such a big mistake. Nowadays, we're measuring with these dim supernovae. The reason why they might be so dim is because there could be all this volume between us, all this distance between us and these supernovae. And you can't explain this large distance with just the gravitationally attractive matter that we know. If, however, the universe had a repulsive quality to it, then it could have pushed these supernovae well out into the universe, so they would appear dim to us today because they're so far away. And that is a universe that fits the data. It fits it pretty well. And it fits it in several different data sets now. So based on supernova cosmology, which was the first to see it, and the analysis of the microwave background, we can pretty much, well, the consensus in the astronomical community is that most of the universe can be explained by a cosmological constant, which is also called dark energy. And this is strange stuff. This is a pervasive type of energy density that repels itself. And, well, it's generally repulsive in the universe and causes the uniform universe to expand. And not only to expand, but to accelerate because it's repulsive. So we now think that our universe is not only expanding, as Hubble found, but this rate of this expansion is accelerating because our universe is dominated by a dark energy that looks like a cosmological constant in Einstein's equations and repels itself, causing this expansion. It also, strangely enough, when coupled with the amount of matter that we think is there, particularly from looking at the microwave background, we think the geometry of the universe is flat. So it's weird. So we have strange energy in a universe that has normal geometry. So in the case of the Earth, we found the Earth was made of just relatively normal matter, but that it was curved when you got out big enough. And you had to consider the curvature on the space of the Earth, on the surface of the Earth, to be important. But things were a little bit different with our universe. We found that the universe was made of stranger stuff, not just the normal rocks and molten matter that might be in the Earth, but that the geometry held up. That 4/3 pi r cubed does explain volumes even further out in the universe. Given that this is true, as I'll explain, the universe will expand forever, and the universe expansion rate is increasing. Therefore, there are three possible ends to the universe. The big freeze is what's called the current favorite that we discussed now. We now think the universe is headed toward a big freeze because we're reasonably confident that most of the universe is dark energy. If we were wrong and the universe was made of lots of regular gravitationally attractive matter, there would have been a big crunch. And as I alluded to last lecture, there's a possibility that has not been excluded that the dark energy is actually part of something called phantom energy, or it looks like dark energy is actually phantom energy. And that is an energy density that is repulsive but growing in time. And if that's true, then the universe will end not by becoming a big freeze, as I'll talk about more at the end of this lecture, or a big crunch. A big freeze because all the matter just becomes so far away from each other that it's just so cold. There's essentially nothing anymore. The big crunch is a heat death that becomes really hot. The big rip is a phantom energy. I'll write that down. Phantom energy dominates. And this phantom energy would create a repulsive universe that would not only create the accelerating universe we see, but any amount of volume would create more and more, would just evolve to have more and more repulsive, gravitationally repulsive energy over time. And eventually that repulsive energy would rip anything apart. And in a finite time, too, in a small amount of time. So that in some big rip cosmologies, which are still compatible with the data, in only a few tens of billions of years or so, the universe would just have so much repulsive energy in it that everything would be ripped apart, and that would be the end of the universe. Now, how is it that we determine things in the universe? We tell it by looking at distant, so we look at supernovae, and these are spectra from different supernovas. Supernovas, supernovae, that tell us how far away they are. And it's supernovas like these that show us that distant supernovas are so far away, they're further away than we expected, and gave us the clue to the accelerating universe. So all of these lines are separate spectra, and all of them have these spectral lines in them. And these spectral lines are shifted relative to our laboratory frame. In fact, they're red shifted. And this red shifting tells us a distance. And this distance, compared to the brightness of the supernova, tells us what kind of universe we might be in. And strangely enough, we're in an accelerating universe so far as we can tell. So here's pictures of distant supernova. Here are galaxies without the supernova, followed by a supernova lighting up. Here's a distant galaxy. There is matter here, but you can't see it very well, but you can see it when a star goes boom. And here's another one, or before and after pictures. Here's the after picture. Star went boom there. So the way this works is, for the Supernova Cosmology Project, is that you look at supernovae that are well out in the universe, that have large redshifts. So down here at the bottom are redshifts. So as you go further out in the universe, you can get a redshift that is bigger and bigger number. In fact, you can see supernova out even past a redshift of 1 now. And you can say how bright these supernovae should appear at this redshift given a certain distance modulus. And so you can plot brightness, meaning distance modulus versus redshift, for different types of cosmologies. So this cosmology assumes no dark energy, and the universe is closed in regular matter. This universe is no dark energy, the universe is open in regular matter, and this is another flat universe, but this has 70% cosmological constant dark energy and 30% regular matter. And so you can see the bottom one is furthest away from this data. And the best fit is actually the top one. And zooming in on it, here you can see just this part isolated here. And you can see they seem to be reasonably well around the omega matter of 0.3 and omega lambda, which is dark energy cosmological constant of 0.7. Okay, so let's look at what we know about the universe, breaking it down. 70% is then that dark energy cosmological constant. 30% is not. So let's talk about this 30%. 30% you would think would just be relatively normal matter, but as I alluded to last time, no, it's not. A common breakdown has most of it being something called dark matter. Now, what's this dark matter? Here we're just getting used to dark energy. Well, dark matter was hypothesized even before, well, was taken seriously even before dark energy was. Looking at the way galaxies rotate like they have a lot more matter to hold them together than we see just by counting up the stars. Also, clusters of galaxies act like there's much more matter there holding them together than we see. So even given that, and even given what's called primordial nucleosynthesis, estimating how much we should be able to get out from the early universe and the microwave background, we now know fairly confidently that 25% of this 30% is dark matter. Of the 30% of relatively normal gravitationally attracting matter is dark. And we don't know what it is. It could be elementary particles. It could be something else. We don't know. Of the remaining 5%, 4% is mostly hydrogen and a little bit of helium. Just out in the universe. It's free. Then the rest of that is stars. And even stars are mostly hydrogen and helium. Then there could be neutrinos. A certain strange type of elementary particle could make up a small percentage. And only 0.03% of the energy density of the universe are heavy elements like you and me. Strange. So, dark matter, what is it? Well, we know that it makes up about 30%, actually about 25% of the universe. We don't see it directly. And to review, we see it in essentially, well, a number of ways, but 3 ways that stand out that I'll review here. One, as I said, is not only in our own galaxy, but in other spiral galaxies, we can count up the amount of matter that's there. And this is even true in our own galaxy. And so if you have the center of the galaxy here, and you have spiral arm here and a spiral arm here, and so you look at things that are far out, and you can tell how fast they're orbiting. We can tell how fast planets in our own solar system are orbiting, and they don't orbit like there's any dark matter there. But when we count up all this matter here, we think, oh, this guy shouldn't be moving so fast. So one way it can be moving faster is if we fill this whole thing in with lots more matter that's dark. It doesn't emit light. Much light, anyway. Light that we can see. Also, clusters of galaxies have lots of galaxies moving around in them. So here we have a galaxy moving here, this moving there, this moving here. These galaxies would just move away and not even care there's other galaxies there if there wasn't dark matter in many of these clusters. So these galaxies shouldn't be there now. They should have dissipated. Why are they there? They must have a lot of gravitationally attractive matter that's inside them, and that is dark matter. And a third way that I'll show you a picture of is that clusters of galaxies are themselves act like gravitational lenses for things far away in the universe. And if all the matter in those galaxies were concentrated in the galaxies themselves and not in the intercluster medium, then we wouldn't expect to see the nice smooth lenses, that smooth background lens images that we do see. So again, looking through a lens is a little bit like looking through a wine glass, but a wine glass is smooth. So if the wine glass is all chunky and had lots of pits in it, then looking through a wine glass at a faraway light, you would see lots of chunkiness. You wouldn't see a nice, smooth, faraway light image. And so by that analogy, we hypothesize that most of the mass of clusters of galaxies are in a smooth, unseen component, which we call dark matter. So hot gas in a cluster of galaxies. So here we have a cluster galaxy. Here's a cluster galaxy. Here's another one. Gas can be stripped out of and these individual galaxies and fall toward the center of the cluster. And here we see colored in red because it emits X-ray light. We can see it, and we can see that it's more uniformly distributed than just around the galaxies. And that is another indication that there's dark matter in clusters of galaxies. Okay, here we see a cluster of galaxies called the bullet cluster. So almost all of these galaxies are points of light, or galaxies. There's thousands of them, easily 100 visible in this image. So here we see where the X-ray gas is mapped in sort of pinkish orange. But mapping how it acts as a gravitational lens, we see that the dark matter is actually separated from that a little bit, which makes this cluster somewhat exciting. So here we see a case where many times, if there's just a centrally condensed cluster of galaxies, the dark matter and the hot gas will essentially trace each other or be similar to each other. But here is a case in the bullet cluster where they appear to be ripped apart and somewhat different. Okay, here is a cluster of galaxies that is acting as a gravitational lens. Here's a galaxy, lots of galaxies in the center. Here is an image of a background quasar. Let's go to yeah, red's good. No, let's color the background quasars in green. So here's one image. Here's another image. Here's another image. Here's another image. Another image. I think there's an image in there too. There's a bunch of images of the same background galaxy. And so these images would not appear so smooth or be in the positions they were if you just took all the mass in this cluster and just put it all right in here. Oops, wrong color. If you put all the mass in here, all right in the galaxies, you wouldn't see this pattern. You have to have more uniformly distributed, let's call it purple. No, let's call it blue because that's what we used last time. More uniformly distributed dark matter here, which might be lots and lots of elementary particles in order to create that distribution. So, dark energy. So what I like to quip is that we pay astronomers and cosmologists to tell us about the universe, and we can't even tell you what the universe is made out of. It's not mostly dark matter due to the cosmic microwave background understanding and supernova cosmology, the supernovas being so dim, and there are other indications too. Most of the energy is some form that we don't know what it is. It's just dark energy, a strange repulsive amount that makes up 70% of the universe. So the way I see it is, one way to see it is this could be useful information. Some people say, oh, well, I study dark energy, you know, there's so little of it nearby. But it could be quite useful. 1,000 years ago, we didn't know, humanity didn't know much about, you know, air or anything like that. Air was, we knew something existed because there was wind, but much about it wasn't known. And people who studied air, people would say, well, why are you studying air? I mean, it's not going to help us. Stop studying that air and do something useful like help the sick, which is, of course, useful to help the sick. But it turns out studying air can be useful for even helping the sick, although not right away. Studying air tells us that air is roughly 70%, let's see, 70% nitrogen and 20-some% oxygen. And understanding air helps us to create things like airplanes. And airplanes help us to move about the planet. So understanding air turns out to be really important, not only for flying about, but for this 20-some%, I forgot I'll put in 25% oxygen, because oxygen is key for people and all living things that we know here on Earth to live. So we need oxygen. We need to breathe oxygen. And if somebody is sick in some way, it might help to give them oxygen. So studying the air turned out to be quite useful. So trying to tell this to a person who lived 1,000 years ago, they just couldn't understand. So maybe we're like that right now with the universe. Most of the universe we now think is dark energy, 70%. And 25% is a type of matter we don't even understand. 25% is dark matter, and we're the rest. So maybe studying dark energy, it might take 1,000 years. I don't know. Maybe it'll take. Maybe dark energy won't be useful at all. Who knows? It might be in 1,000 years we'll be able to find a use for it, and it might be interesting. It might be tremendously interesting. We don't know. It's this wide open basic science right now of just trying to understand it. One of the main pushes in astronomy now is trying to figure out, is this dark energy constant as you go out in the universe? Maybe dark energy was different in the early universe than it was today. Maybe it evolved in some way. And so we're trying to study supernovae and other distant things of the universe, star formation rates, gamma ray bursts in the distant universe, to try to find out if dark energy was any different back then. Let's see, repulsive gravitational effects seen. Okay, yes, I covered all of that. Okay, getting into the future of the universe. Let's say that the universe is, as we suspect it is now filled with mostly dark energy. The matter and even dark matter will become a smaller and smaller fraction of this as the universe goes on, and we will end in a big freeze. What happens on the way to the big freeze? Well, right now we're in what's called the Stelliferous era, where the universe is filled with stars, is lit up by stars. This fraction of the energy density, although a relatively small fraction, is in stellar light. Stars are being born even today. We've seen lots of pictures of them in this course. Eventually, though, in billions of years, the Stelliferous era will eventually come to a close, and there will be very few bright stars, even as bright as the sun. Then we'll be in the degenerate area, where most of the stellar things in the universe, and even things emitting light in the universe, are the stellar remnants of what came before. These would be white dwarfs, the neutron stars. They would fill up most of the universe, the brightness of the universe. There would be black holes around, but they would still be relatively rare. Eventually, many of these things would collapse, or they would become collapse. They would fall into other black holes, the centers of black holes and the centers of galaxies. Or they would just become so dim they wouldn't be of interest anymore. It's possible that the protons in them would decay, and so they would no longer be there, and the universe would just be filled with radiation and black holes. And it would be called the black hole era. As Hawking had indicated, and we've now believed this is true, even black holes can evaporate. And if you have a black hole, and there are virtual particles somewhat created around the black hole, one can fall in that has essentially negative mass. Don't worry about that. Positive mass gets to infinity. The black hole then ends up with slightly less mass than before. And the more massive the black hole, though, the longer it would take to evaporate. But a very small mass black hole would evaporate in essentially an explosion. But eventually, all black holes would evaporate, and you would be just left with light. And this light would be redshifting, forgot the D, and the universe would be in a dark era where there would be nothing left than energy that's redshifting. Mostly light. There could be some neutrinos, I guess, redshifting. And I'll close the lecture, but not the, we'll have astronomy pictures of the day next, with the Big Rip era. Here is just a artist's rendering of the universe, a galaxy being ripped apart by a supposedly phantom energy that dominates the universe and just comes to push everything including ourselves, apart. Okay, so I will now move over to the astronomy pictures of the day for the past week. We will minimize, and we'll go into the, okay, let's see, I don't know, did we do bubble and Cygnus? It's been looked at, but I'm not sure why. Okay, so here we have a bubble in the constellation Cygnus, and this is probably a bubble around a type of star called a Wolf-Rayet star, which are interesting because they might be involved in the creation of tremendous explosions called gamma ray bursts. But they're certainly energetic endings to very massive stars. And as they go, they create, let's go to blue here, let's go to red, they create bubbles. And so this is a previously unknown bubble. So in this era of where technology allows amateur astronomers to image wide parts of the sky to relatively faint magnitudes, this isn't possible with big telescopes, because big telescopes only see very small portions of the sky. And they don't have the time to really look at wide portions of the sky very deeply. But amateurs do. And so this is something that an amateur discovered. This Cygnus bubble doesn't even have a number. So remember, we've talked about things by NGC numbers or Messier numbers or IC numbers. This is too new for that. Hopefully we'll be given a designation by the International Astronomical Union relatively soon. So right now it's just known as a faint bubble around a star in Cygnus. Okay, so going to the next one. So we live in another era where we're able to find stars around planets. So Fomalhaut, no, actually it's pronounced Fomalhaut, sorry, is a star that's visible primarily in the southern hemisphere, 25 light years from Earth. It's only visible in the southern hemisphere, and it's been studied. It's been known to have a dust disk. So most recently, images have been taken. Here we see an image in 2004, another image in 2006, and there is a point here inside this disk that's moving. Oh, there it is. So that is thought to be a planet. And if so, this is one of the first imaged planets ever. There was one that was appeared on Astronomy Picture of the Day also in September, and there will be one we'll see in a few pictures that appears today, given it being Monday, although actually being broadcast on a Thursday. So Fomalhaut is seen to have a star, and this is exciting because we're very interested in finding Earth-like planets, knowing how unique our solar system is in the universe. So actually being able to see a planet, before we knew there were hundreds of planets, the way we knew they were there is because of very slight shifts in the planet, in the star itself, in the slight red shifts and blue shifts. But here we can actually see the planet exists. Oh, also we knew because planets would sometimes eclipse the star and cause a slight dimming. So it's very exciting to start getting actual images of these stars themselves. Okay, so this is Interacting Galaxies from November 15. This is, remember, last lecture we tried to type galaxies. This used to be some kind of spiral. This is another kind of spiral that's spread out. And ARP made a catalog of many of these. This is the 273rd entry in that catalog. So this is being studied as interesting ways that galaxies can interact with each other. Okay, I'm actually not going to be able to go through all the astronomy pictures of the day for this week, because it's actually Monday and not Tuesday and Wednesday, although I do know what Wednesday will be. There's only one more past this one. This is very interesting. This was sent to us. This is a rerun. So we do best ofs or reruns on weekends. And this is a picture of something that seems to be happening over the horizon. This is taken in Colorado. And here are cows. These are ordinary cows that are not actually part of the illusion. And it appears that there's these tremendous light coming out from the horizon. But what's actually happening is these are something called anti-crepuscular rays. And the sun is setting behind the head of the photographer. And then light rays travel on they travel in straight lines. But straight lines, when mapped onto the sky, become great circles. And great circles, when you take a globe and you draw great circles tend to intersect on, like a basketball, on ends of the globe. And so that's what's happening here. On one end of the basketball globe is the sun setting through clouds. And on the other end, sunlight is coming down to create sort of a collision, a apparent collision of sunlight on the other side of the projection of the celestial great circles onto the sky. Okay, and I will close with the two discoveries were announced in the same week. This is not only an image of 3 planets, but it is an image of planets in a distant star system, HR 8799. But this one has multiple planets. It's even cooler. The central star was blotted out. So what you see there is just noise. The star has been removed, but they couldn't remove all the noise. But the planets stayed around. So here are planets that glow in infrared. This one is labeled D, it's the closest one in. This one is labeled C, and this one is labeled B. And the arrows show the direction of motion. So you can there's actually data that shows these planets orbiting the central star, which you can't see. So this is the first, imaged planetary system other than our own. Previously, there were systems that showed multiple planets, but they weren't imaged, or they had a Jupiter-sized object orbiting inside the orbit of Mercury. Here we see these are outside the orbit of Neptune, all of these. This is roughly the orbit of Neptune there. This is out even further, those two. So it's a unique system, and finding systems like this gives us hope that there could be orbiting in here, maybe an Earth-like planet, because this is a sun-like star. This star in there is 1.5 times the mass of our own sun in 8799. HR is the name of the catalog. So there could be an Earth-like planet inside of there. It's certainly something that might be looked for. And this also gives us general hope, even outside this system, that there are lots of systems similar to our own solar system where Earth-like planets might exist. So even during this class in fall 2008, astronomy has expanded. Things are being discovered all the time, and now we're actually able to image. We're imaging planetary systems that are not so different from our own. So hopefully within our lifetimes we will be able to image an Earth-like planet, and people are working very hard toward that. So I will review the next two for Tuesday and Wednesday in next week's time, and I will conclude there. So I will see you next week.